All right, ladies, so we're going to look at an example of a two-dimensional motion with momentum. So in this scenario, we have a ball traveling 2 meters per second west, strikes another ball, same mass, and then each ball heads off in a particular angle, okay? Now, question like this, I'm going to ask you, what is the initial momentum along the x direction? So we're going to talk about 2 dimensions here, right? So what's the initial momentum along the x direction? Well, it would have to be the first ball. So what would be the momentum of the first ball? It would be m1 v1, which is 0.1 times 2. So that's a momentum of 0.2. We know the unit is kilogram meter per second. I'll leave the units out. West. The second ball is stationary, right? So what's its momentum? Would be 0. So what's the initial momentum? Well, it has to be then 0.2 west. Okay? That's the initial momentum. One ball is moving, the other one's not. Now, what's the initial momentum vertically? 0. This ball has no vertical, I mean along the y-axis, okay? There is no momentum in either this direction, up or down, or that y direction for both. So that the initial momentum in the y direction is 0. Now, conservation of momentum means that the momentum has to be conserved. We have the angle. Okay, we're told that each ball has an angle of 20 degrees, correct? Okay, so this is what we're going to do. Let's look at the momentum along the x. The momentum along the x has to be 0.2 west. Right? Let's think about the components of that momentum. For the first ball, it would have to be its mass, m1, times its speed, but we don't know what the speed is, but times the, well, what would that component be? Cosine of 45. So in other words, it's this component of the momentum of this ball, plus that also the same component for the momentum of the other ball. So that would be m2 v2f times cosine 20. Okay, so let's simplify this. So 0.2 west equals ball 1 times its speed. So what's cosine 45? 0.71 times 0.71 plus ball 2 times its speed. What's the cosine of 20? 0.94. Okay, so let's simplify this a little further. So 0.1 and 0.71 add up to multiply and become 0.071. And this becomes 0.094. So there is our equation for the horizontal. Okay? It's 0.2 equals 0.071 v1f plus 0.094 v2f. Okay? Now, let's look at the vertical. So the vertical initial was 0, right? Which means we have a momentum we can see acting, we'll say up. It's not really up, but we'll just say up on the screen from ball 2, and we have one component acting down from ball 1. But those two have to add up to what? 0. So we could say that ball 1 times its final speed times the sine of 20 minus, because we're going to add, but it's adding a negative vector, minus the second ball times v2f times the sine of its angle. Oh, sorry, it's the other way around. It's m2. It's m2 minus m1. You're right. Yeah, this is m2. That's m1. Yeah, because this is ball 2. Ball 2 is going up in north direction. Ball 1 is going down in the south direction. So it's actually supposed to be m2 minus m1. So it's m2. So it's this component minus this component. Good catch, Alvin. Yeah, let's change everything then. This. Okay, let's just rewrite it then. We gotta change everything then. Let's rewrite that. Okay, so it's m2 v2f times sine 20 minus m1 v1f sine 45. Now let me save us a lot of headache there, otherwise we'd be fighting in the end here. Okay, let's put in our numbers. So it's 0.1 v2f. What's the sine of 20? 0.34 minus 0.1 times v1f times 0.71. So we have 0.034 v2f minus 0.071 v1f. So now we have two equations. We have this equation and we have this equation. I'll call this equation A. I'm going to call this equation B. What do you think we should do here? And what does this now look like? Does this not look like the scenario with the poles where you have static equilibrium and you're trying to resolve the forces in the poles and you have the angles and you know that the net force horizontally and vertical is 0 and then you substitute one into the other? This is exactly the same. So what we're going to do here is we're going to isolate for, we'll say V1F. So V1F would be, so it's going to be, if we move this over to the other side, it will be negative 0.034 V2F over negative 0.071. That is a negative sign. Awful negative sign. So then, let's simplify. What is V1F equal to? 0.48 V2F. So now we have what V1F equals. So what we can do now is we can plug that into this equation up here. So let's do that. So 0.2 west equals 0.071 V1F. But V1F is 0.48 V2F plus 0.094 V2F. So we have 0.2. We know what's going west. I'll leave that out. So what does this add up to? 0.0 plus 0.094 V2F. Okay. What is V2F then? So this is going to add up to 0.034, 0.094, 0. So it's going to be 0. What is it? 0.12. So it's going to be 0.2 over 0.12. So V2 is 1.56. I'm just going on for 1.6 meters per second. Sorry? Yeah? Okay. And then V1F is 0.48 times V2F. So 0.13. And then what's V2F? Is it 1.6? Okay, 1.5. That's okay. We'll round it up to 1.5. And then, so now what's V1F? So V1F is 0.48 times V2F. So what is that? 0.48 from here. We isolate for what V1F stands for. So what is that? 0.72? Okay. Alright, so the technique to solving a question like this is actually the same technique you learned with static scenarios with forces. Remember we did questions with poles and cables, so it's actually the same. So this is saying that ball 2 is heading off at a speed of 1.5 meters per second, and ball 1 is heading off at a different direction at a speed of 0.72. All right. I'm going to stop it there.